Our next unit is going to be over an idea called electrostatics. And we're kind of moving out of the realm of all the rest of these waves and sound and light and things like that, and kind of getting into this idea of charge. And what we'll end up doing with electrostatics, well, first off, just break down this word a little bit. Number one, we got electro and we got statics. What does this mean? Well, electro is charge. Let me move that out of the way. Electro is charge, and statics is in place, okay? They're not moving yet. Now, they will move under certain circumstances, but right now we're looking at charge in place, okay? Where do these charged objects come from, okay? Well, a charged object has an uneven number of protons and electrons, and you become charged by either gaining or losing these electrons. A lot of times you'll see me write that just as an E negative, okay? That's just where it comes from. I guess I learned that a long time ago, and it's just where it works, okay? So you become charged when you lose electrons. You're not going to lose protons. Protons are on the inside of the nucleus, on the atom. They're held together by the strongest forces, I think, that we know about. The protons aren't moving, okay? The electrons on the outside, those guys are moving, okay? These electrons have a charge of 1.6 times 10 to the 19th coulomb. And we'll get into what a coulomb is in a minute. But it's the unit of charge, okay? It's the unit of charge. So you become charged by losing or gaining an electron. If you lose an electron, right, if you lose your negative, all of a sudden you're positive, right? If you gain an electron, plus E, now you're negative. You lose electron, you are positive. Some basic fundamental laws. You remember this from chemistry. Opposite charges attract, like charges repel. Opposite charges, there's a plus and a minus. Like charge, what are you? Either minus a minus or a plus and a plus. Okay? Charges, the other cool thing about this, and we haven't gotten much into any of these forces and whatnot, but these charges can act on each other at a distance, okay? You don't have to touch something to transfer charge or charge somebody else up, okay? Once we get into more electricity and electric currents after this unit, electrons move a little more easily through conductors like metals. Why? Well, that has to do with the number of electrons on those outer shells. Okay, electrons do not move easily through insulators, plastic, wood, rubber, glass. Okay, then the difference between these two usually is the electron configuration on the outside. Okay, metals have electrons that like to move on those outer shells. Okay, I don't know if we're going to get into it. Let me go back just a second. There was something, I don't know if you remember, your generation kind of takes this for granted. There's something called a semiconductor. What does that mean? Well, semi means half. There are things called a semiconductor that are sometimes like an insulator and sometimes like a conductor. Okay, and these semiconductors basically can be turned on and turned off, right, and have electrons move through them, and then they can shut down. Okay, this is the basic. These semiconductors are basically the fundamental parts of computers that TI put together back in the 60s, late 60s, I believe it was. Okay, but a semiconductor is part-time conductor, part-time insulator. Electrical laws. There's one big law here. It's a conservation of charge. Just like everything else, we've had conservation of energy, conservation of mass, conservation of momentum. Okay, charge may be transferred from one object to another, but it's not going to be created or destroyed. Okay, how you transfer it is another story. Just like some of the other things, there's a couple different ways to look at it. Excuse me. You can charge it by conduction. Conduction, contact. Okay? An example, the static electricity from your feet rubbing on the carpet. Okay? You're actually transferring electrons from the carpet to yourself. Okay? Conduction, contacts. The other way, induction. Okay? You can rearrange the electrons on a neutral object by bringing it close to a charged object. Okay? So what you do is you don't have to touch it, right? But since you know that opposites attract, if you have a balloon that's all of a sudden all negative over here and some other object, you know, you don't have to touch this rod or a piece of cloth or whatever, or your clothing, right? If you make one side basically negative, electrons don't, opposites attract, like charges repel. The electrons basically move over to the other side a little bit, which leaves this side as positive. Okay? So you can charge it up just by being close by. You rearrange those electrons on the outside. Okay? Then you can get a static discharge. Okay? This is, pictures of clouds and things like that. When you get a transfer in the air because of a buildup of electricity, okay? You have the ground is basically neutral, and what can happen in these clouds here, right? The clouds are up here. This is a dark picture for me. I can't see this real well. Okay? What happens is these clouds, these electrons up here, right, start to move around. Okay? And once you get a big buildup of charge, whoop, where did it go? You get a big buildup of charge, and we can use this, look in the background. You get a big buildup of charge, it's going to jump, from negatives, 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 and it's going to jump to the ground. It's going to look for something. Okay, that's why if you're in a thunderstorm, you don't want to be up high. Trees get hit, right? They're the highest thing up. They're looking for something to jump to. We can detect a lot of these things with something called an electroscope, and you're going to build one of these for us. Okay, an electroscope is simply a device that shows whether or not there's a charged object around. Okay, and you usually have a glass. Here's a glass flask. Okay, there's a ball here, and then down you have two little metal strips. Okay, and then one of the things you look at, number one, it's going to be neutral to begin with when there's no charged objects around. Okay, it's going to be neutral when no charged objects are around. Wow. Let me go back then. Okay, and what's going to happen, that if those leaves here become separated, right? If those leaves become separated here, are they like charges or opposite charges? Well, if they're separated, like charges repel. Okay? And we're gonna test some things out and get some of these things done. So when you have a negatively charged object touch the electroscope, okay, when you actually touch this part here, right there, okay, you touch that ball, well then the electrons jump off and come down into here, okay? Those become likely charged, they repel. Okay? The other way that we represent some things is with electric field lines. Now, what we end up doing with electric field lines is, remember, negatives right there have electrons coming towards them. Positives are losing their electrons, okay? So they become positive, okay? So when you draw these field lines, you're going away from the positive and towards the negative, okay? That's why here, when you have like charges repelling, these lines here that come in, these are repelling each other. These field lines don't cross, okay? over here, you have your field lines going directly from the positive to the negative, so you get an attractive force. Okay, just remember, away from the positive and towards the negative. Okay? You get field lines, okay? Basically, the more field lines you have, the stronger you are. Okay? So when you're nice and close over here, these are strong. Okay? These are going to be relatively weak. Okay? Here's a question for you. The way these are drawn, are these positive charges or negative charges? Which way are the arrows going? The arrows are going away. If the arrows are going away, are you positive or are you negative? Okay? Away from positive. So these would all be positively charged, wouldn't they? Okay? Grounding. Okay? We've all heard about being grounded. Well, when an object is grounded or there's grounding going on, you're basically removing excess charge of an object and removing it to something like the Earth, or usually to an object that's a substantial size, okay, to where it's not going to be affected by the excess charge. The Earth is so large that almost any charge can flow into it, and it's not going to make a difference. The electric potential, and we'll get into that as well a little bit later, is still zero. Okay, but grounding, that's what the third, if you look at your plugs, that's what the third metal piece is on a plug, on a lamp, or on anything, really. I think all things now have 3 on them. Now, you knew we were going to get into math to do. It's called Coulomb's law. Okay, Coulomb's law, and basically it starts talking about the electrostatic force between 2 charges. Okay, what do we know? It's proportional to the magnitude of the charge, Q1, Q2. We got 2 charges. Remember, this is the force. This is the force that occurs between any 2 charges. Okay? That force is directly proportional to the charges, right? And inverse square to the distance, right? We've seen this before. Okay? As distance goes up, the force goes down. Okay? As distance goes up, the force goes down. And it goes down with the square of the distance. K is a constant, 9.0 times 10 to the 9th newtons meters squared per coulomb squared. Okay? It's just a constant. It's not going to change. It's not going to change. I was just trying to see who's there. And hopefully you remember the structure of this formula. Where else have we seen the structure of this formula before? Okay? Where have you seen the structure of this formula before? I'm going to put something in here. We haven't talked about that. We're going to put in a page real quick. Okay? And if you look at Coulomb's law, okay, what do you have? That force electric, is equal to what? K, Q1, Q2, all divided by distance squared. Okay? Take a look. Where did we see this before? Gravity. Okay? That force of gravity equals what? Big G, M1, M2, all divided by D squared. Okay? You see the commonalities here? We still have a constant in play. It's not that constants don't matter, but structurally they don't when we come to a concept. Okay? Whereas gravity was determined by the mass of those objects, right? Coulomb's law deals with the charge of those objects, but it's still an inverse square. Okay? So if D goes up 2 times, what happens? the force goes down 4 times. Okay? Same rule still applies. Excuse me. Okay? If D goes down 2 times, your force goes up 4 times. So what would happen if the distance went up 3 times? Well, if your distance goes up 3 times, you now have 3D squared. Your force is going to go down 9 times. Okay? And we'll get into this a little bit more, but conceptually I wanted you to see how the structure of these two formulas is common. Okay? Which is actually, to me, is really pretty cool. Okay? So what happens? When you double the distance, the force drops by 4. If you double the charge, okay, if you double each charge in this case, it would go up by 4. Whoop. That might be all for now. Okay, folks, thanks for listening.